This podcast talks about orbital diagrams and how to draw them and what information they give you, and we'll also talk about valence electrons, which will be useful later for bonding. So orbital diagrams are the same information that we get from an electron configuration, but they also talk about spin. So they show how many paired and unpaired electrons there are in each orbital. Hund's rule, this is useful for showing magnetic behavior. Hund's rule says that each orbital gets one unpaired electron, and then we go back and we add a second one to each orbital and pair them. So one way to think about this is like seats on a school bus. When students are getting onto a school bus, every student gets their own seat until all the seats have one student, and then they'll go back and pair up. So the correct way to write this, if you have 6 electrons to put into the 1s and then the 2s, and then 2 more electrons to put into the 2p, they are going to go 1 into each orbital. Remember that the p orbitals have 3 orientations, 3 orbitals. Each orbital is going to get 1. By convention, we always write spin up first. That's just what everybody does, so that we all do exactly the same thing. This is correct. This is incorrect. You cannot put 2 electrons into the 2p orbitals, pairing them before each orbital gets 1 electron by itself. So let's do sodium. First thing, I'm going to write the entire electron configuration first, and then write the orbital diagram. Alright, so when you go to write orbital diagrams, you do not have to write the electron configuration first, but it can be useful if you're stuck. Sodium, neutral, has 11 electrons. Its electron configuration, 1s2, 2s2, 2p6, 3s1. So each s orbital is going to get one line, because one orbital. When we get to the p, it's going to have 3 orbitals, so it's going to get 3 lines and hold 6 electrons. So for sodium, instead of just writing 1s2, we write 1s, 1 line, 1 orbital, containing 2 electrons, and they have to be opposite spin. 2s has 2 electrons. The 2p has 3 orbitals, total of 6 electrons. It goes up, 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 1, 2, 3, down, down, down. They're all filled, so we keep going. And then the 3s orbital has 1 electron. Because it has at least 1 unpaired electron, we say that sodium is paramagnetic, which means it can be attracted by a magnetic field, and that's because it has unpaired electrons. It doesn't matter how many unpaired electrons it has, it's paramagnetic if it has at least 1. So for the next 3 elements, write the orbital diagram. If you want to write the electron configuration first, you can, but you do not have to. Write the electrons as arrows and figure out if it's paramagnetic. Shut off the video and work on these, and then turn it back on and check your work. Okay, so phosphorus, which has a total of 15 electrons, has 3p3, so these 3 electrons do not have pairs, so phosphorus is paramagnetic. Cobalt, which has 27 total, has 3d7 electrons, so 7 electrons in the 3d orbital. Remember that the d has 5 orbitals in this sublevel, so it's got 1, 2, 3, 4, 5 going up, 2 more, so it has 2 that are paired, but because these ones are not paired, it is again paramagnetic. Magnesium has 12 electrons total. In the 3s orbital it has 3s2, so it has both of them paired, and therefore magnesium is diamagnetic. It has no unpaired electrons. Valence electrons are electrons in the highest occupied energy level. They're important because they're the ones that are used in bonding. So when we get into bonding, we're going to talk a lot about valence electrons. So this is just a preview on how to think about valence electrons along with electron configuration. So we're going to write the electron configuration for selenium and figure out where the valence electrons are and which ones. So here's selenium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. The highest occupied energy level here is 4. Remember that we're going to start filling 4 before energy level 3 is completely filled. So it's 4s1, 3d10, 4p4. But the electrons in the fourth, which are 4s2, 4p4, those are the valence electrons. So selenium has 6 valence electrons. The 3d10, third energy level, not the highest, not valence electrons. So just the s and the p electrons are going to be valence electrons. And that's true in every element. A handy way to write valence electrons is to use the electron dot diagrams. And again, this is something that we're going to use a lot when we get into bonding. It indicates the number, just the number of valence electrons. Those are the only electrons that we write. The way we write it is we write the number of dots to show the valence electrons. Because they are the highest energy levels, they're always going to be just the s and p, not the d electrons, not the f electrons. And it can have up to 8, because s can hold up to 2, p can hold 6. That's a total of 8. And to be honest, this is actually where the octet rule comes from. So we'll do lithium. Lithium has 1 valence electron, so we write 1 dot. Nitrogen has 5, and we write the dots. We give each side 1 dot, kind of like electrons that are not paired. So it goes 1, 2, 3, 4, and then we pair 5. Fluorine has 1, 2, 3, 4, 5, 6, 7. So it has a total of 7 valence electrons, so it gets 7 dots. Argon has 8 valence electrons, and you can see this is why argon is a noble gas. Doesn't want to bond because all of its valence electrons are filled. Carbon has 4, and again we write them unpaired, 1, 2, 3, 4 by convention, and this helps us to figure out bonding later on. So this is a useful feature for electron dot structures when we get into bonding.